All right, let's talk about applications of separable equations. The first thing is Newton's law of cooling. So this is what Newton thought about. The rate of change of the temperature of an object. So capital T is the temperature of an object. Lowercase t is time. Should be proportional to the ambient temperature. So if you had a very hot soup laying on a table, the rate of change of the temperature will have to do with how cold the room is, right? If the soup was left outside where it's freezing cold, it will be cooling down much quicker, right? So this is how he wrote it down. He said, well, assuming that ambient temperature is some constant that doesn't change, then the difference between the ambient temperature and the temperature of the object is going to be proportional to the rate of change of the temperature. So in this model, if this difference is big, so for example, if you put something cold in a hot environment, if A is very big and T is very small, this will be positive. This will be increasing very fast. That's what's going to happen inside an oven, right? So this is what Newton said. Now, can you turn this into an equation? How does that work?
Multiply by the right side by k.
You multiply the other side by k, and now you have an equation. And that is the equation that governs heating or cooling of an object inside an ambient temperature where ambient temperature is fixed. Okay? So let's think about the following question. A frozen pizza initially at 32 degrees Fahrenheit is put into an oven that is preheated to 400 degrees Fahrenheit. Okay? The pizza warmed up to 50 degrees in 10 minutes. How long would it take to reach 200 degrees Fahrenheit? Okay, I just pulled up these numbers out of thin air, so I have a bad feeling that it's going to be too long. It's maybe an hour, so it's not realistic. But let's just see what happens to this one. Okay? Yeah, I think what's gonna happen is really this should be much smaller.
Yeah,
You know, let's
like
change
2.
it. Maybe it's more like 2 minutes. Okay, then it's probably more realistic. Okay, so in this case, and then I guess what they're trying to do is this is where you can actually take the pizza out and eat it. So the target temperature is this. So how long does it take for the pizza to cook? That's basically the question. Let's try to answer this. Okay, solution. So we have change of the temperature equal to K times ambient temperature, which is 400, minus the temperature. But this is your ambient temperature. Now you can treat this as a separable equation because if t was like y and small t was x, you can move this to the other side and you can divide the entire thing to the left side, and you would get a function of t, y only, and a function of x only, right? So this is a separable equation. We can solve this using the exact technique that we learned. So let's divide this to the other side. Equals to k times dt. What next? What do we do?
Integrate.
Integrate. Yeah. The right side is easier. Let's do this first. What's the integral of k dt? kt. Let's see. Now this one, let me tell you another very handy formula you should memorize. If you have f prime over f dx, that's same as ln of the denominator plus c. In other words, if you take the denominator and if you differentiate it and that happens to be the same as the numerator, then the integral is just the ln of the denominator. Now I want to apply it to here because, I mean, if you don't use this formula, you have to end up using the u substitution. That takes too long. I don't want to do that. Okay? I just want to take a shortcut. However, here it's not true that the derivative of the denominator is the top. If you differentiate 400 minus t by t, what do you get? 400 differentiates to?
0.
This differentiates to 0 and minus t differentiates to -1. So overall you get? -1. This is positive 1. So what do you do?
ln of 1.
Negative ln.
You put a minus in front and put a minus in front.
Oh.
Then everything works out, right? Now you have the derivative of the denominator same as the top. Okay. With expense of this minus in front. Okay. Now, after having this, what's the integral of the left side?
Negative ln.
ln of?
1.
Yeah, 400
Oh, plus
minus t.
Okay.
kt plus c. I could have put an absolute value, but according to this formula, the situation here, temperature is always less than 400, right? So therefore, this is always positive, so I don't need an absolute value. So this is what I have. All right, and then we can now solve for t. How do you solve for t, for capital T? First, multiply by negative, so you have ln 400 minus t equals to negative kt minus c. And then you raise both sides with respect to e because e and ln cancels. After canceling the e and ln, I have 400 minus t equal to e to the negative kt times e to the negative c. I want to split this exponent into two because if you remember, this is just some arbitrary constant, right? So we're going to use that trick of rewriting this as some constant c tilde. Okay. That makes calculation a lot easier. So we have 400 minus t equals to e to the negative kt times c, where this c is really c tilde, which is e to the negative c. Yeah, we still haven't isolated t by itself, so to isolate, I should move the t to the other side and move this to the other side. So 400 minus C times e to the negative kt equals to T. So I have the solution, the temperature at each time T. I raised the problem, but we had additional data. So we have that if T is equals to 2 minutes, what's capital T? What did I write?
50 degrees.
50 degrees. So let's use this to figure out what K is, or C is. I don't know. Yeah, I guess we can figure out what. Okay, let's plug in and see what we can get. Okay. So we have 400 minus C e to the negative 2k equals to 50. Oh, there's another thing that we forgot to use. When T is 0, what was the initial temperature?
32.
32. That's the thing that we forgot. So for that one, we go back. So there was one investigation. For the second investigation, we set T equal to 0. And that's better for us because now you only have C. C times e to the 0th power, and initially was 32. So that gives you that C must be moving C over there and moving 32 over here. We get 368 as our C, and therefore if I plug it in here, I get, plugging this in here and solving for K, this is what I get 400 minus 368 e to the negative 2k equals to 50. Let's attempt to solve this for k by moving the 50 over here, moving that over here. So we get 350 equals to 368 e to the negative 2k. Divide both sides by 368. And then you get 350 over 368 equals to e to the negative 2k. To get rid of e, you take ln. That cancels, and you get negative 2k equals to ln of 350 over 368. And finally, to get rid of negative 2, to isolate k, you have to multiply by negative 1/2 ln of 350 over 368. Okay. Now let me use Google to figure out this. It's a negative log of, usually when you say just log, let me see, I think in Google if you just say log, it's log 10 is 1 here. I guess they won't. Okay, we're good. All right, so if I do negative ln of 350 divided by 368 divided by 2, I get the value 0.02507. K equals to 0.02507. Okay, we're still not done yet because we have to find out when it reaches 200 degrees.
What is K considered?
Huh?
What is K considered?
K is proportionally constant.
Okay.
See, it has to do with the material that you're heating. For some materials, the rate of change will be very fast. So if you put a metal into the oven, the metal will be heating up really fast. Right? And for some other material, it will go up, the heat temperature will go up gradually. So if K is a big number, then it means it heats up fast. K is a small number, it heats up slowly. That's basically what it is. Okay? So what you get is that T is now 400 minus 368 e to the negative 0.02507 times T. All right. With this, we're trying to ask, when does it reach 200? So now we have the equation to solve for T. We have 200 equals to 400 minus 368 e to the negative 0.02507 T. And let's subtract 400 and divide by negative 368. That gives you 200. If you subtract, it's negative 200 dividing by negative 368 equals to e to the negative 0.025070. To get rid of this e, we have to take ln, and therefore t would be obtained when you divide this value by this value. Okay? So it will be ln of 200 over 368 divided by negative 0.02507. All right. So let's see if the numbers I started with were reasonable. Usually pizza takes about, what, 20 minutes, 25 minutes to cook? Yeah.
Yeah.
Hopefully it's reasonable. Let's see. ln of 200 divided by 368 divided by 0.02507, and it's 20. Wow, I'm good. So you have t equals to what, 24.3 minutes. And the pizza is ready. So that's it.